Okay. Looking at 2C from last night's homework that you've already started on. If you haven't already started on it, at least look at it. Start forming your thoughts on what are you going to do. Because I'm not going to tell you what to do. Absolutely not going to do that.
It's from right to left. Or on the y-axis, so they just changed it to the y. It's going to be from 0 to whatever that y is.
I'll tell you from walking around, I have not seen a single individual who has correctly set this up.
Oh, if I need that point, yeah. I thought it would be this point.
Until now.
Well, then this point, look. It's 4. 4, 4. That point is 4, 4. Remember that?
You don't need it. You don't need the video for anything. Those are the first 2 parts. No, from this homework? None of the
Yeah,
stuff
so
that we
this
learned.
is what it has to. All right, so let's have some good conversation about 2C. I will tell you, if you ask any of the Calculus BC students, this was the hardest one in this problem set when they had to do it. Hello, Anthony. You just happened to stop by? You knew I was going to say something about Calculus BC students? What are some tricky things that we're encountering so far? I'm not going to tell anything. I'm just going to ask really good questions. What are the things that are making this problem challenging? Adriana's got some stuff. I worry that it means that some of you guys are not looking at this clearly enough. Adriana, what are your thoughts on 2C? What's going to be a challenge here?
It has to be in terms of y. It is being revolved around the y-axis.
Okay, we're revolving around the y-axis, and as soon as you know that you're revolving around the y-axis, that means everything is a dy kind of integral, because your slices are going to be going this way. So whatever you do, it has to be in terms of dy. And Jonathan has it solved beautifully. He has it one way, but there's like lots of different ways. So that's the thing that's going to be challenging. What else is going to be challenging? See, if we don't have the conversation now, then you guys are going to go home and you're going to hit all the challenging stuff there, and it's going to get ugly. What are the things that are making this problem challenging?
You're looking for volumes, you have to have the right equation.
Okay, definitely we're doing a volume problem, so you need to make sure you have the right kind of equation. Is this object hollow or solid?
Hollow.
Oh,
Hollow or solid? Hollow. I've heard some solids.
I say hollow.
Depending on how you look at this, it's both. There's a part that's solid, and there's a part that's hollow. If I look at taking this region here, remember the way that we would draw this, you draw the reflection. So like, there's the line, there's the curve, and you say, okay, like here's my little rectangle, here's the reflection of the rectangle. Down here, hollow or solid?
Solid.
Wait, down here?
Solid.
Solid. Up here? Hollow. Well, hollow?
No.
No, I think I just drew it badly. Right, because it goes up and then it kind of goes that way. So down here, everybody was convinced solid. Over here? Solid. Up here? Hollow. For the first time, we've got a shape that is solid for a part and hollow for a part. What I need you to do is have a good conversation. What's your plan? How are you going to handle this solid-hollow combination?
Oh, that's the point you're talking about. Define that piece separately as the solid and then the other piece.
separate equation.
So a lot of the conversation seems to be focused on dividing this into two different parts, right? If you are solid for a part and hollow for a part, then how about if I draw this line and say, okay, below the line I'm solid, above the line I'm hollow, find the volume of this part down here, find the volume of this part up here, and then add them together. Is that gonna work? Absolutely. Absolutely. So if I want to find the volume of, let's say, the solid part, well, it's going to be pi. I need to integrate from a place to a place. From where to where?
0 to
From, I want to be careful with the 0 though, from y equals 0 up until
Y equals A.
y equals a, or can we be more specific?
2.
Right, this guy over here is the point 0, comma 2. So we're going to go from y equals 0 to y equals 2. I need to figure out how long is that little slice. Well, if that slice is on the line, which is the line y equals x, how long is the slice?
Right minus left.
How long is the
Right
slice?
minus left.
You're going to do right minus left. I'm on the line y equals x, and I'm going all the way over to the y-axis. So it's just going to be not x, but y. That's what's going to get squared dy. Plus, now I need to figure out the volume of the hollow piece. The volume of the hollow is going to be pi. I'm going to do an integral from a place to a place. I'm going to start at y equals 2. And then I'm going to have to figure out the intersection point, wherever that is. For this top part, because it's hollow, your integral has to look like a big R squared minus a little r squared, but it has to be done in terms of dy. That's about the extent of the help that I'm going to offer on this problem right now. But is everybody okay with this? We got a solid part and we got a hollow part. Never dealt with this before. One other option that some students might consider, and this is not really the way that my brain works, but some folks say, let me pretend that this whole object is solid all the way up to the top. And what they'll do is they'll say, all right, let's do an integral from y equals 0 to wherever this place is, and if I'm pretending that it's solid, just use your slice, use your like y squared dy slice all the way from 0 up until this point. How do we feel about that? Is it going to give you the right answer?
Yeah.
If you assume solid all the way from 0 up until this horizontal line, is that going to give you the right answer?
No.
No. Oh no.
If all I do is
Subtract.
do this, what's going to happen? Are you going to get the right answer if you go from 0 all the way up here using this solid idea? Why not? Daisy, why not?
Because you're counting all the area in between.
Not area,
I mean the volume.
volume. You're counting all of this stuff that's not supposed to be there. You're saying it's included in the volume, and I don't want to do that, so it's your option.
Subtract.
I'm here, what are you going to do?
Can you just subtract R, the area you find for R?
Not the area.
How do you do that in R?
The volume, you're going to say, let me find the volume of this part over here as it gets spun around, and just scoop it out. So you're saying like solid minus another solid from y equals 2 to whatever, something squared dy. This option works just fine. This option works just fine. Either way is fine. And Jonathan, nice job. Everybody okay? We're good with the things? Jasmine, you all right? All right, so here's what I want to do. I want to give you guys 5 minutes, see what you can do from yesterday. If you're Jose, if you're Jennifer, maybe friends near you will adopt you. We're going to go totally calculator active on this first one. I want to see what you guys can do with this one. David. Nora. Lauren Shear.
Extraordinary amount of things. I know this is great, but what I do with today.
Jose. Strongly recommend we make scroll to make corrections.
I agree.
John, Christian, Abraham. Go tell the mama.
So what is Nora software?
Oh, Albert.
He did, like I keep telling you about.
One back on one. Oh, I have already gone into on my own. Wow, this is Jennifer O.
All right, y equals 4x minus x squared, I think, looks like that, right? All right, there's the base, right? Jose, the plan is always like, draw the base. So my base is 4x minus x squared. It's the part that's in the first quadrant, so it's here, it's this part. Taking perpendicular to the x-axis. Sorry, perpendicular to the x-axis. Which way? Right, which way? Oh, Mariah, you've got the Jedi sword. Right, if I'm going this way, dx or dy?
Don't chop off the light.
Right, if it's perpendicular to the x-axis, this is where like the BC kids were always like, dx! Because that was like their judo chop noise. Okay, so dx is the thickness. How tall? Well, that's what I'm going to call L, and L here is 4x minus x squared, so I'm going top minus bottom. After you figured out the base, now we're gonna look at the slice. So I need the slice. What's the slice, Edgar?
Wait, what?
The
Oh,
slice.
it's, right, I thought
Edgar, can I have the slice?
oh, my bad.
Remember the slices that I gave you and said, hey Edgar, can you hold the slices? Hey,
No.
please, you didn't do any
My
better.
bad.
You didn't do any better. Okay, right isosceles triangle, one leg on the base. So I'm looking something like this, right? The triangle's coming out of the board. I'm gonna lay it down flat just so I can draw it because I am artistically challenged. There it is, right triangle, those are equal. L, L, I got a little thickness here. There's my dx, volume of the slice. Area of the base. L times L, cut it in half. Volume of the slice is a half L squared dx. We went from the base, we've got the slice, the last piece. What's the volume of the solid? How am I going to find the volume of the solid?
I need
How are you going to find the volume of the solid, Norma?
The integral
Oh.
1/2
1/2.
4x parentheses 4x minus x squared
4x minus x squared squared
times dx.
times dx. The last thing that I need? Need my limits of integration. What are the limits of integration going to be?
0 to 4.
We're going from 0 to 4. Rambeer, what'd you get for an answer on the calculator?
Where did I get for?
What did you get for an answer with the volume?
Oh, actually, we did.
I thought you guys were just having a conversation over there. What's the volume that we're getting?
I ain't that fast.
Hello?
34.1.
Okay, I feel like one person's even trying to get the volume on their calculator.
Oh wait, no, I was wrong.
What's the volume on the calculator?
I'm wrong.
Juan, what's the volume on the calculator?
17.0667.
Yeah.
17.0667. How many of you guys are honestly getting 17.0667? All right, so I'm pretty convinced.
I got 34.
You got 34. I think you're missing a half.
Yeah.
Okay? But the process is going to be the same. You figure out the base. I will always tell you about the base. Always. I have to tell you the base. Then you're going to figure out the slice. Your options are, humor me for a little bit. We're on camera here. Make sure you're ready for this. Okay, parallel to the x-axis. So I'm parallel to the x-axis. Parallel to the x-axis. We're going this way. What kind of interval?
Side side. Oh, dy.
dy or dx? dy. That's right, dy to judo chop. Okay, perpendicular to the x-axis. Which way?
DX.
dx. Parallel to the y-axis. dy. And perpendicular to the y-axis.
Isn't it dx? If it's parallel to y.
Parallel to the y-axis dx. Thank you for making me take one from somebody.
Yo,
Okay, what did we say? We said parallel to the y-axis. So dx, perpendicular to the y-axis. Perpendicular to the y-axis. dy. There you go, not diagonals. No, we're not ready for the diagonals. Okay, so
it's diagonal.
here's the thing. Yes, there's all the things. Here's what I want to do. For the next 15 minutes, I want to focus on the slice. What you're going to find is once you figure out what the slice looks like and how to find the volume of the slice, everything is easy. Right? If you've got the base, you've got the slice. Once you've got the volume of the slice, you get the volume of the solid and you're done. Okay? I would expect most of you guys should be able to come up with the volumes for 1, 2, and 3 pretty much on your own or with minimal help from me. For the sake of Jose and Jennifer, I'm going to go through and do the first one. And I'll do it with you guys and anybody else that wants to. But 15 minutes from now, the goal is we are done with 1, 2, 3, 4, and 5. Just focus on the slice. All right. So, number 1. For whatever my base is, the squares are parallel to the y-axis. So Jose, Jennifer, anybody else that wants to play along, show me parallel to the y-axis. Parallel to the y-axis, we're going this way, right? What's the shape? I need squares. Edgar, hook me with the square. Okay, so we're saying that the slices are squares parallel to the y-axis. They're coming out of the board, right? So if that's the way I think about my little slice, I'm going to have that little sliver. That's what I'm going to call L. How thick is it? If it's this way. That's a dx. When I actually ask you to draw the slice, what we're going to do is we're going to say, oh, take this and lay it flat. So I'm going to have a square that's got a little bit of thickness. If this piece over here is L, then that piece over there is L, and the thickness has to be dx. I've made my slice. It's a dx kind of square slice, and I'm just laying it flat so I can see the slice. What's the volume for a slice? It's base times height and your thickness. So L squared dx is the volume for one of these little slices. Jose, are you okay with that? Don't lie. So there's some base that we're making all of these little slices with. The height is what I'm calling L, the thickness is dx, but when I lay it down I get to see, oh, the height is L and so is this part over here. The volume of a slice is L squared dx. What's the volume of the solid? What does Riemann tell you to do? The volume for one little slice is L squared dx. The volume for the solid? Jennifer, what's the volume for the solid going to be? You need an integral from some place A to some place B. I don't know what the A and the B are, and it doesn't even matter right now. Okay, and what's the integrand? It's L squared dx. You do all the work on the slice piece so that the solid part becomes easier to work with. Okay? All right, so Jose and Jennifer and anybody else who wants to play with me. Semicircles with the diameter on the base, perpendicular to the x-axis. Semicircles. Perpendicular to the x-axis, we're going this way, right? Semicircles. Can I have a semicircle? Semicircle. Perpendicular to the x-axis. So right now I'm just drawing this little guy here. I'm saying there's L dx. When I take my semicircle and I lay it down, this guy over here is L. It's got a little bit of thickness to it. I need the clever geometry, folks. What's the volume for the slice? It's the volume for one little
Pi r
slice.
squared. Half pi r squared.
Right, I'm hearing a lot of half of pi r squared, because, right, you would do like full circle would be pi r squared. What you've got here is you could say, oh, well, the volume of the slice is a half of, there. A half of pi r squared, but be careful, that doesn't get you volume, that just gets you area. There's a little bit of thickness,
Dx.
so you're going to multiply by the dx. Okay? Now there's a problem here.
Half L.
The height that we're talking about is L, but to find the area you need R. What's the relationship there?
2R equals L.
Right, if L is going from this side all the way over here, L is going from here to here, you guys have a different word for that, right?
Diameter.
That's your diameter. L is twice the radius, so the radius is a half of L. That means the volume for your slice is a half of pi times a half of L, the whole thing squared, dx. It's ugly, that's fine. If you want to clean it up a little bit, let's do some legal mathing. 1/2 of L, you're going to square that. We're going to have a half of pi times a fourth of L squared dx. If I clean that up, I'm going to have 1/8 of pi L squared dx. Volume for the solid, this should hopefully be the easy part. If that's your slice, now you do an integral. 1/8 pi L squared dx from A to B. Jennifer and Jose and anybody else who's with me on this. What questions are out there? One.
Just a clarifying question, is the L equals to R, that's because that would be, the L is the diameter, right?
Right, because for the semicircle, the L represents diameter. And when your area formula, you guys all told me right away it was 1/2 pi r squared. Radius is going to be half what the diameter is. All right, well, keep going. You don't need me. Keep going. I want to get 1, 2, 3, 4, and 5. Jonathan.
So that means that would be that squared
Would it be what squared?
for the
This guy here?
for the integral. So would that squared? Which area?
No, because we've already got, the L is already getting squared. Right, this expression here is telling me the volume for a slice. To get the volume of a solid, it's just a matter of integrating the whole thing from A to B. Okay? Edgar, can you get rectangle? Thanks. All right, Jennifer, Jose, and all the friends. Rectangles with a height which is 1/3 the length of the base, parallel to the x-axis. Parallel to the x-axis. Which way? Parallel to the x-axis.
dy.
If I'm going this way, so it has to be dy. It has to be a dy. So whatever that length is, I'm just going to call it L, and it's dy. There's the rectangle. Now there's something special that they've told you about the rectangle. They're always going to have to tell you something about the rectangle. If you know that the length is L, well, what's the height?
1/3 the length.
Right, the height is 1/3 of L. They're going to always have to tell you something about the height. So when I take my rectangle and I lay it flat, if this is what I'm going to call L, then the height part of it is going to be 1/3 of L. The thickness part is going to be dy, and so the volume for this one slice is 1/3 of L times L times dy. Right, so just 1/3 L squared dy. Volume for your solid is going to be an integral of 1/3 L squared dy from A to B. Okay. Focus on the slice. Make sure you know, am I slicing this way or am I slicing this way? Find the volume for that slice, then use it to set up the volume of the solid. Okay, keep going. 4 and 5 are going to be... So what kind of integral? Has to be dx if you're slicing this way. Alright, Andrew, can you hit me up the right isosceles triangle? And Mariah, which way are we slicing? Parallel to the y-axis, so I'm going this way. There's L. When I saw in just about all the papers, everybody's got a dx integral. Okay? So now it's just a matter of tell me about the slice. If I make a right isosceles triangle with a leg on the base, this is L, that's L, and your thickness is dx, volume for the slice.
1/2 L squared.
1/2
dx.
L squared dx. Now that I figured out the volume for the slice, the volume for the solid, it's going to be an integral of 1/2 L squared dx from A to B. Once you understand the slice, everything falls into place. Everything falls into place. Questions about any of these first four? All right, so we can do with the last one. This one is definitely the hardest one. One more time. You lost me at the L cubed. Okay. All right, equilateral triangle. Equilateral triangle, one side on the base perpendicular to the x-axis. If I'm perpendicular to the x-axis, dx or dy?
dx.
dx, good. All right, and what I saw on pretty much every paper that I saw was, all right, so here's my slice. I know it's going to be L. I know it's going to be dx. Here's my equilateral triangle with one side on the base. Great. Draw it over here. Now here's where things get ugly. Equilateral triangle. What do we know?
All
Jasmine, what do
sides.
you know?
All the sides are equal.
All the sides are equal. L, L, L. It's got a thickness of dx. The problem is this. I keep seeing on all the papers that the volume of the slice is 1/2 of L times dx, or in some cases, we're even throwing in an extra L just for the L of it. Okay? Not the way you find the volume of this triangle. The way that you find the area of a triangle, everybody knows. Base times height divided by 2. Where's the height? For this triangle, where's the height? If this is what I'm calling the base, the height is not here. The height is not here. Where's the height? If this is the base, the height is perpendicular to the base, meaning that the height goes here. That's the piece that you need. Now, figuring out the length of this gets a little bit tricky because you need to think about some trick. You need to do some right triangle trick. If all 3 sides are equal to each other, you also know that all 3 angles are equal to each other, so 60, 60, 60. Okay, that slice there, if it's going to be truly perpendicular, then it makes a right angle. That's 60, that's 90, this angle over here has to be 30. If you've got a 30, 60, 90 triangle, there's a relationship that you know has to be true. If this guy over here is L, then the length of this part right here across from the 30 is 1/2 of L. Across from the 60, This guy over here is going to be the square root of 3 over 2 times L. It's your 30, 60, 90 triangle. L, half of L, square root of 3 over 2 times L. So when we have conversations about what's the volume of the slice, well, it's a half of your base times the height times dx, and if you multiply that out, you're going to get square root of 3 over 4 L squared dx. So when you get over to the volume of the solid, it's going to be an integral from a to b, square root of 3 over 4 L squared dx. Hit me with the questions. You guys are too quiet to not have questions right now. Edgar.
What happened to the L that was with the height? You know how it was square root of 3 over 2 times L?
Uh-huh.
What?
That's this guy over here, square root of 3 over 2 times L.
Why didn't it go to the equation?
Why didn't it go to the equation? It did, because the way that you find the area for this triangle is it's a half the base times the height, half L square root of 3 over 2L.
Oh.
And those guys get multiplied to get square root of 3 over 4.
Oh.
Okay. Now here's a reason that I just wanted to do these 5 in a row. If you look at all 5 of them, go back to the very beginning, look at the volume of the solid, you might start to notice something.
L squared.
All these volume expressions are not actually that different. Every single one of the volume expressions looks the same, except for one thing. The constant. So when you're looking at the square, the integral, right, the integrand is just L squared. L squared dx or dy, limits of integration. What if it's the right isosceles triangle? Right? When it's the square, when it's your square slice, everything's just L squared. Right isosceles triangle? 1/2 L squared. Semicircle.
1/2 pi.
Careful, not 1/2 anything. 1/8 pi, and then the L squared. The equilateral triangle.
3 over 4.
Square root of 3 over 4, L squared. The rectangle. Don't fall for it. Don't fall for it.
1/3.
Don't fall for it.
1/3.
Don't fall for it.
1 over
The rectangle.
1/3. Oh no, no, nothing. No,
Everybody
nothing.
keeps telling me 1/3.
No, that only applies to that.
It
No.
depends on the rectangle.
Yeah.
If I tell you that the height of the rectangle is 5 times the length, then this is L and this is going to be 5 times L, and it's going to be 5L squared. So one more time. If it's the square,
L squared.
L squared. What if I'm parallel to the y-axis?
L squared.
L squared dy or L squared dx?
Dx.
Parallel to the y-axis.
L squared
dx.
L squared
dx.
dx. Right isosceles triangle perpendicular to the y-axis. Right isosceles triangle
1/2
perpendicular to the y-axis.
1/2 L squared dx.
Right isosceles triangle is 1/2 L squared, and then it has to be dy because you're going this way. Semicircle perpendicular to the x-axis. Perpendicular to the x-axis dx. Semicircle.
1/8 pi L squared.
1/8 pi, pi over 8. Equilateral triangle parallel to the y-axis.
square root of
3 over 4
Has to be square root of 3 over 4.
dx.
What did I say? Parallel to the y-axis? Dx. Look, your life just got so much faster. Let's do one of these really quick. Life just got really good, and I don't think you guys even noticed it got really good. Okay, let region R be the area enclosed by y equals x squared and y equals 4. Using region R as a base, a new solid is formed. Cross sections perpendicular to the x-axis are equilateral triangles with one of the sides along the base. Determine the volume of the solid formed. You've got 3 minutes. friendly base here. Y equals x squared. Y equals 4. There's the base. Which way are the slices going?
dx.
They're perpendicular to the x-axis, so it's a dx. Great. There's that length. There's dx. Abraham, can you tell me how long is L going to be? It's going to be what? How long is that slice going to be? Sorry, Edgar's got a big head. I can't see it.
Oh, I mean,
How long's the slice? If I'm starting on the line y equals 4 and going all the way down to the line the parabola y equals x squared, how long's the slice? It's going to be 4. Careful, I'm not going down to the x-axis. I'm just going down to the parabola. So it's going to be 4 minus x squared. Now normally at this point you guys would go over on the side and say, oh, well now I've got to draw my little slice. There's L, there's L, there's L. They're all going to be dx. How many of you guys know what the volume of the slice has to be?
Square root of 3 over 4.
Equilateral triangle. What does the volume have to be?
Square root of 3 over 4.
Square root of 3 over 4.
L squared.
L squared.
dx.
yeah.
dx. I don't want you to go through the whole, well, it's going to be half of L, and this is going to be square root of 3 over 2. You know that the volume set up is square root of 3 over 4 L squared. What's the volume of the solid? Volume of the solid is just going to be the integral of the square root of 3 over 4. Take the L that Abraham gave us, 4 minus x squared squared, dx, from where to where?
Negative 2 to 2. Negative 2 to 2.
I heard 0 to 4. I've heard negative 2 to 2. From where to where? Okay, we're going to go from this intersection point over here to this intersection point over here. So it's going to be x equals negative 2 to x equals positive 2. Pop into the calculator, tell me what you got. If you spend a little bit of time really understanding the slice, everything becomes a piece of cake. What'd you get, Edgar?
14.7802.
Okay, Edgar's offering up 14.7802. Anybody else get 14.7802? Kristen's got it, Giselle's got it. Abraham, we're good. That is a way to go about doing this. I'm going to show you guys one thing that's going to catch you by surprise, possibly. One of the things they like to do on the AP exam is they're going to ask you for the setup only. Right? And so you might say, oh, well, that's easy. Here's my setup. I'm doing from negative 2 to 2, square root of 3 over 4, 4 minus x squared squared, dx. If they just ask you for the setup, what are some things that could be done to hide this answer from you? Right? Because think about those like, it's option 1 only, it's option 2 only, it's option 3 only. What could they do to hide this answer? Not the final answer of 14.780. What are some legal things that could be done here? Giselle, what do you got?
The squaring it.
Squaring it. So maybe they multiplied this out with the box, right? 4 minus x squared times 4 minus x squared. Great. What else? Legal things that they could do. Ron Beer, what can you do?
Move the square root of 3 over 4 outside.
Why can you do that?
And it's a constant.
Okay, that square root of 3 over 4 is a constant. And so you say, okay, there it is. How about this? Martin, what were you going to offer?
Doing 2 intervals.
2 integrals. Tell me more about these 2 integrals.
Continue from negative 2 to 0 and from 0 to 2.
How about even better than going from negative 2 to 0 and 0 to 2? What if I just say, you know what, I'm just going to integrate from 0 to 2. Square root of 3 over 4 or 4 minus x squared squared dx. Right? Don't bother going all the way from -2 to 2, just go from 0 to 2.
Multiply that.
And then double it.
Oh.
Tell somebody near you why that would actually work. There's something special about the base. The key with the base, if I've got the line y equals 4, if I've got the parabola y equals x squared. David, what's the key?
It's an even function?
Okay, y equals 4 would be even, y equals x squared is even, but the base is symmetric, right? It's balanced across the y-axis. So whatever volume I'm getting to the right of the y-axis has to be exactly equal to the volume I'm getting to the left of the y-axis. And so you might use the symmetry idea to make life a little bit easier. All right, show me what you guys can do with the next one. And feel free to use the calculator. Base. You've got to understand how the base and the slices work, David, before you make it all the way over to the interval. Where's your base? The base is the flat thing that you're building on top of. Like in this last problem, we're looking at the base as the region bounded by y equals 4 and y equals x. Here's the base. Okay, so that's not going to work so well for you. Yeah. If you switch the x's and the y, then you're switching the direction. So now you're graphing it thinking it's a parabola that looks like that. That's absolutely not what happens. Okay, so I love the fact you said, okay, x squared y squared minus 4, so let's switch it. That you made the scary mistake. The expected one, the scary one. You added 4 to both sides, and then you took the square root of it. Plus or minus. Which means that you get this part up here, and you get another one down here.
Oh,
Okay, so it looks like when you're graphing it, you're solving for y. Plus or minus. So you're going to have a part that's up here and a part that's down here. All right, so for folks that are in the Tuesday group, I will see you guys at 4:15 to 5. We're working on AP